Yep, no, so we are ready. So welcome everyone to the first HEP-TN Seminar of 2021. We had taken a short break, but now we are back. Please check our website, hep-tnseminar.org, for information about upcoming seminars. Today we are very happy to have Norbert Schuch to kickstart our seminars for this year. And today he is talking about entanglement order parameters from symmetric tensor networks. So Norbert, thanks a lot for giving this seminar. And please take it away.
Thanks a lot. Thanks for having me, and thanks, Suki, for your insistence in inviting me. So I recently moved to Vienna, so the last months were pretty busy, but finally things are back on track. And I'm very happy to give this talk. I would say I'm more happy to give it in person, but this has always been an online seminar. So in this case, this doesn't apply, but it would certainly be nice to give talks in person again. Okay, so what I would like to talk about is how to construct order parameters, measure order parameters, which include conventional order parameters, but which are a more general class of order parameters, and which I think are constructed in a very natural way if you have tensor networks and if you think of the symmetries which these tensor networks have. So one specific application, and actually the motivation for us, or the direction from which we came to do this work, was looking at topological order and asking, can we construct order parameters which allow us to study properties of topological phase transitions? But I think the overall theme is more general, and I would really try to present this talk from this more general perspective. So it's indeed the first time that I'm trying to present this from the more general perspective, and then only put the topological order in the second half of the talk. So I'm curious how this will be going. So as I said, this was our motivation, but I think in the end, it's a more general story, which is, I think, worth exploring. And most of this is based on joint work done with Mohsen Iqbal, who was a postdoc of mine until recently at the Max Planck Institute of Quantum Optics. Okay, so so this is about order parameters, and well, I will talk a bit more about order parameters on the next couple of slides. I might say things which are completely obvious, but maybe also not. Maybe I will present some things from a different perspective. In any case, you should feel free during the whole talk to ask questions if you have any. So local order parameters are a very powerful tool, as we all know, right? They allow us to distinguish, to identify different phases. So for instance, we can take some magnetic system, and at high temperature, it will be disordered. So it will have the full rotational symmetry. At low temperature, the magnets will order in parallel. So these local order parameters can be used for different things. They can be used to identify different phases. They can also be used to probe properties of the phases, to study the phase transitions. And so, as I said, our motivation came from the direction of topological order, where there's a lack of local order parameters, right? That's basically the definition of topological phases, is that there are no local order parameters to identify them. And this is linked to the fact that there's not necessarily any physical symmetry linked to that, right? So no physical symmetries, no local order parameters, but there is order which manifests itself in global properties, right? For instance, in the degeneracy of the ground state, which cannot be, so these ground states cannot be distinguished by local order parameters. Usually I can look at the possible values the order parameter can take and conclude the number of ground states from there, right? So it doesn't depend on global properties. Here it depends on global properties. And these systems usually have exotic excitations with exotic statistics. Again, this is some global property, because statistics is seen when you move things around each other in very big loops, for instance, right? So it must be something which is not seen only locally. So it means these systems must exhibit some global structure, some global ordering in their quantum correlations, in their entanglement. And this was our motivation, where we came from. How could we identify and probe such topological phases? And well, when I mean identify and probe, well, what can order parameters do? So what roles do order parameters take? So one role order parameters take is to identify, to distinguish different phases, right? I would say if the magnetization is non-zero, this is a ferromagnetic phase. If it's zero, it's a paramagnetic phase, right? But on the other hand, order parameters, as we very well know, conventional order parameters can also be used to make quantitative statements. So we can study how the order parameter changes as we approach a phase transition and extract signatures of universality, right? We can look at critical exponents, at scaling exponents, and we can see that maybe different types of physical systems all fall into the same universality class, right? So we can understand features which are universal to this transition independent of microscopic details. And in some sense, for conventional order, one doesn't really distinguish these two things, but I think it's important to make clear to yourself that there are these two different meanings of the word order parameter when we talk about it usually. Because if we look at topological phases, things are somewhat different because there are indeed quite a number of qualitative order parameters, of qualitative probes, which allow to tell us, which allow us to tell if a certain system is topologically ordered, and also which phase it takes, right? So we can look at the scaling of the entanglement entropy and look if there's a topological correction, right? We can do things like look at the SNT matrix, so the braiding matrix, which we can compute using tensor network methods, right? Renormalization-based methods. But all of these are really just indicators which tell us yes or no. So they tell us you're in this phase or you're in that phase, but they will not allow us to make a qualitative statement, really. And the reason is that in the end, they're defined in the thermodynamic limit, in the IR, right? When we take things far apart. And now, if we want to study quantitatively topological phase transitions, there's actually not so many probes, right? Or there's really a scarcity. So there's duality mappings, but of course, then you need a duality mapping. And once you don't have a duality mapping, you're a bit lost. So that's not something which allows you directly to probe the system. It's more a reasoning by analogy. One can look at entanglement spectra at criticality. There have been works looking at things like the scaling of the gap, which gives you some partial information about universal behavior. But it really only gives you some combination of the dynamically critical exponent and some other critical exponents. So it can maybe disambiguate certain phases, but it's not the full information. It's less than you would like to have. And this is basically what we would like to address, or that's where we're coming from. So to see if we can devise quantitative order parameters for topological order from the point of view of tensor networks. And by quantitative, I mean things which are suitable for instances, the quantitative study of the order parameter close to the phase transition to extract critical exponents, universal behavior, and so on. But in the end, what I would like to, the way I would like to present it in this talk, and I think the way one should really look at it, is to ask, so topological order is related to order in the entanglement, right? And tensor networks very naturally provide us access to the entanglement. And a general question would be, can we use this direct access to the entanglement degrees of freedom in the tensor network to access additional information about phases of general quantum systems? So this includes kind of really quantum matter type phases like topological phases, but this could even include conventional phases. Maybe there's more we can discover by also looking at the entanglement. And I would really like to present it from this more general perspective. And then tensor network topological order is one very natural application of this. But I think actually it also opens up some new ways. This perspective of thinking about order parameters through tensor networks helps us to maybe also open up some new routes in conventional phases. Okay, so I'm going to say a few things about order parameters, which probably mostly are well known and obvious to all of you, but I will also point out a few things which are maybe obvious, but it's not clear that they're important. And in some sense, they're only important once we think about tensor networks. So I think it's worth going through that. So the key prerequisite for local order parameters is some symmetry. And I'm not sure if I should always call it a local or a global symmetry, but given that this is a high energy seminar, I think you guys would call it a global symmetry, right? So it's a symmetry acting everywhere, but it's a tensor product of local operations, right? We're not talking, we're not talking about a symmetry which acts globally like time reversal, but which acts individually on each system. And as an example throughout the talk, I will have the Ising model. So for instance, we could take this Ising model here on the right, and the symmetry would be flipping all spins simultaneously, right? That's the symmetry of our system. And once we have such an such a symmetry, we can construct an order parameter by basically picking any operator, any generic operator, which does not commute with a symmetry. So in the Ising case, which anti-commutes with a symmetry. So for instance, we would take a Pauli Z, right? But actually, a linear combination of Y and Z would also be good, with one exception, which is non-generic, right? So what we want is that an order parameter should transform like an irreducible representation, right? So when we conjugate it with a unitary, when we commute it with a unitary symmetry action, we get some non-trivial phase, right? In the abelian case, certainly. And like Z anticommutes with X. And then just from symmetry considerations, we can immediately tell that if we have a symmetric ground state, so in a system with a unique ground state in particular, this order parameter, the expectation value of the order parameter will be 0. Whereas in the other case, when there's a degenerate ground state, we generically expect it to be non-zero. Also, it depends on the state we take. And we can make this more robust by looking at two-point correlation functions. If we have a method which actually gives us symmetry-broken states, it's not necessary. But in the end, it's somewhat a safer option because it will not depend on which state we pick, right? If you do quantum Monte Carlo at finite temperature, you will not get a symmetry-broken sector. That's what you do, for instance. And we will see the same behavior there, right? This will go to a constant. Maybe I should have called this C squared, really, because it's the square of this expectation value. If that's C, the other thing is C squared. So we will see that as we separate these two operators at 2 points in a 1D chain or in a 2D lattice, this is not dimension specific, right? This will either go to 0, exponentially, presumably in a gapped phase, right? Which will tell us that this is disordered, or in the other case, that it's ordered. Now an important point is to see where we really only want to think about symmetries. We don't want to say we have the Ising model. I use it as an example, right? But I don't want to be focused on this is the Ising model. I want to be focused on saying this is a model with this symmetry here. And if that's the only thing which I'm allowed to use, then there's no specific way to pick this order parameter, in fact, right? I could pick any alpha z plus beta y, and they would have the same anti-commutation relation, and they should all be fine, and they are all fine, except for only y, right? So basically, any operator transforming as that irreducible representation is good. The reason we pick Z is because Z is kind of the extremal object at the renormalization fixed point, right? At zero field. But there is no other reason really to choose that one. So this can also be said as creating an excitation, right? As flipping a spin in the disordered phase. Again, we could choose something which creates a nice eigenstate at infinite field, and that's what we do, but there is no specific reason for doing so. Okay.
Excuse me. So why should it transform this order parameter as a irreducible representation? I would think that a non-trivial representation would be
indeed,
sufficient.
Indeed. I mean, well, that's a good question. Presumably, yes. There should be distinct sectors and you should be fine, right? No, I agree. But in the end, I mean, the sharpest order parameters will be the ones which are one irrep, right? Everything else will be kind of a sum of O alpha plus O alpha prime.
Yes.
Irreducible representations. So then presumably you see if you look at the correlation function of this with itself, right?
Mm-hmm.
Probably the conjugate representation, you will see that the only terms you will keep is this one and that one, if you look in a symmetric state, right? Because the other one don't transform like a trivial irrep. I mean, the good thing about this thing is that it transforms like a trivial irrep.
Yeah. No.
That's what you want, kind of, if you want to be sure that even if you take a symmetric count state, which you will get if you use a symmetric tensor network, for instance, gives you the proper result. So in the end, there's no big difference, right? You would just get the sum of the two, but indeed, it's not mandatory.
No, indeed. But indeed, I could imagine that things conspire against you if you have a bunch of irreps.
Well, but things even in the irrep conspire, because if you put a y here, right, it will also be 0 in the Ising model. So anything which is non-generic, we drop, but that's very normal, right? I mean, you want to know if there's an obstruction, like a symmetry obstruction, or in topological order, people would say a topological obstruction, which forces things to be 0, right? If they're not forced to be 0, we'll basically anticipate they're non-zero, unless otherwise we were fine-tuned.
Yeah. Okay. Cool.
Right? So same here. I presume that this is completely fine because that these two terms cancel is very unlikely, but you don't gain anything, right? So it makes our life easier if we focus on the case where we only have one irrep.
Yeah.
Okay. Good. Now that's actually not the only order parameter we can construct from symmetries. We can also construct a dual order parameter, or what people often call a disorder parameter or disorder operator, which in a one-dimensional chain would be a finite string of symmetry operators. So for instance, in the Ising model, it would be a finite string of Pauli X operators. And what happens? Well, if we're at low field, such an operator will flip part of the spins, right? So it will create an orthogonal state. It will create a domain wall. So these two states will be orthogonal, right? So the expectation value of this operator in the low field regime will be 0. In the high field limit, right, this x will not do anything because I'm in an eigenstate. So I will get a non-zero value. So what we see is that this string operator will now be a constant, which is not 0 in the disordered phase, but it will go to 0 if I make this very long in the ordered phase, right? And the point is that even if I'm not in the cliché all spins up state, at the boundary there might be some overlap, but as I go into the bulk, the spins actually will be orthogonal from some RG point of view, maybe. So the string will flip spins. It will create an orthogonal state even away from the fixed point wave function, from this cartoon wave function, and I will get 0 as I separate these a lot, right? If they're close by, this will not really happen. And again, this is not unique. It looks more unique than the irrep. The irrep before, if I had degenerate spaces of my symmetry group, were extremely non-unique. This looks unique because I can just say I pick the symmetry, but you could dress the endpoints with some operator which transforms trivially under your symmetry, right? So for instance, you could try to dress the endpoints to create something which is an eigenstate of the dynamics, right? Because these domain walls will be that dispersing objects if you're not at a fixed point. But again, that's usually not what is done for an order parameter, and there's a good reason. We freeze these points to be an operator which has some fixed, which corresponds to the fixed point. So I should indeed say, I think I will stress this again in the next slide, but it's actually essential that we don't try to make operators which are too naturally suited to each specific value of the field. Because for instance, we could ask, can we find something? Well, let me say this on the next slide, maybe. Right. So this is actually dimension specific here, right? So the string operator makes sense in one dimension. It will not have the same effect in 2 dimensions. But in 2D, we can do something similar. We can take an area and say apply a sigma x in the Ising model on the spins in a certain area and ask what happens. And again, you will flip spins, right? And if you're in a ferromagnetic phase, you will create a penalty which goes like the volume, right? If the spins are not perfectly aligned, you're at finite field, they have some angle. So you will get something which goes down exponentially with the volume, right? And in the ordered phase, it will also go down exponentially because the boundary will still create some defect, but in the bulk, because it's disordered, you will not have changed your state. So you will get a boundary law, right? So what you will get is that this is a 2D disorder parameter, which distinguishes 2 regimes through the scaling Wilson loop type, right? A volume law versus a boundary law scaling, if you compute its expectation value. Right, so what do we assume when we look at these order parameters and change our field? Oh, good point. One thing I just wanted to say, I didn't want to give it an own slide, so it just pops up. We had order parameters, we had disorder parameters, so we had irreps, we had strings. We can actually combine them, at least in 1 dimension. And what we get are string order parameters. So that's actually already something which detects non-trivial types of phases. Right? It detects symmetry protected 1D phases. And it's very natural to combine these 2 things, right? Because if you have one thing which works well, another thing which works well, why not combine them? So for all these things, there's no reason not to combine 2 types of order or disorder parameters. Right, so what happens when we look at these things? So we have an order parameter, so that's, say, the Ising model, right? So we have some magnetic field, which we increase. And we can look at the order parameter, which will either go to a constant or exponentially go to 0. This is the ordered phase, right? The other thing is a disordered phase. And the disordered parameter does the opposite. It will go to 0 in the ordered phase and to a constant in the disordered phase. And if I plot the square root of this constant, right? So what corresponds to one of these operators or one endpoint of the string, I will see that my order parameter goes to 0 as I approach my phase transition. The disorder parameter is 0 in the ordered phase and will start to become non-zero in the disordered phase, right? Then I can also extract a correlation length here from the 2-point correlation function, right? So I will have a correlation length because the correlations decay to 0 in the disordered phase. Exactly, but from the disorder parameter, I can also extract a length scale. So I can extract some dual length scale in the ordered phase. And for all of those, I could compute critical exponents, which allow me hopefully to say something interesting about the phase transition, right? And in principle, these could all be different. There's a priori no reason why these things should be the same for a general model. At least I don't see a general reason. Now, one thing I would like to stress is how should we construct our order parameters? And this is one of the points where you will say, why is this guy talking about this? Because somehow for normal order parameters, it's obvious, but we will see later for tensor networks, in some sense, it's a very non-obvious thing. Or, well, basically here, it's obvious what is the right thing to do. In the tensor network situation, there is no right thing to do, which is obvious in some cases. So how should I choose this? Well, we could try to choose these operators, or also the endpoint of these domain one operators, to always form some particularly nice state, something like which is always an eigenstate, right? Or which always maximizes the order parameter, right? I mean, I could say I have some ambiguity. The thing has to transform like an irrep, but I don't know like which irrep, right? It could be anything. And there's no rule that it has to be a single side operator, right? It could be a 5-side operator, which transforms like an irrep on those 5 sides. So can't I try to take this operator and maximize the value of the order parameter? And then you will see that you can actually improve quite a lot, right? And if you don't restrict the range on which this operator can act, then it actually becomes completely pointless, because you can just adiabatically evolve your order parameter, quasi-adiabatically evolve. You will get an operator spanning something on the order of the correlation length, and it will always have the same expectation value, 1, right? So this is something you don't want to do, right? You don't want to optimize this. So you don't want to make this depend on the field age, or if it does, it should depend in a very nice analytic bounded way. And this is something which is kind of obvious, that you don't want this to change with a magnetic field in a weird way in this case, but we'll see that in tensor networks, that's an important consideration. So that's something I would like to stress, right? It's on purpose that order parameters are not constructed to capture exactly the physics at each value of the field. They're constructed to capture, for instance, the physics at the RG point. It's not essential, it's the RG point, but you want something which is fixed. Or if not, you want something which maybe changes nicely analytically with the field, because then it doesn't matter, right? Because in the end, you look for the non-analytic behavior at the critical point. But you don't want something which is kind of tailored to be, say, an eigenstate at each value of the field, because these eigenstates will have a size on the order of the correlation length, and they will spread out. And then you will get things like step functions. That's not what you want. The situation is less tricky for the correlation length, because you indeed expect the dominating correlation term to always be the same independent of which operator you choose if it's generic, right? Okay. Any questions? I haven't yet talked about tensor networks. Okay, let me talk about tensor networks. Well, I guess everyone here knows tensor networks, given it's the tensor network seminar series, and also looking at the list. So I will look at 2D tensor networks. I will look at square lattice tensor networks, and I will look at translation invariant tensor networks, right? So we have one 5 index tensor. Oops, I realize I have to erase what I wrote before. So we have 1, 5. That's what happens when you stare at the preview screen, because on the preview screen it doesn't show what I drew. So I was like, nice new slide, but there was all the drawings. Right. So I look at square lattices. It's not inherent what we do to square lattices. It's just so much easier to draw them that it's favorable to draw square lattices. Exactly. Bond dimension is capital D, but we rarely need this. So I guess everyone is familiar with tensor networks, right? If not, please show it now. Right. So what we would like to study with tensor networks is models which have symmetries. So we were talking about order parameters. As I said, order parameters are closely linked to symmetries in systems. So how do symmetries show up in tensor networks? Well, one thing is if I have a global symmetry, so a symmetry which acts on every side the same way, like UG tensor N, I can encode this in the tensor network. And the typical encoding, it's maybe not the most general one, but it's good enough for our purposes, is that each physical symmetry here corresponds to a virtual symmetry action, which is a tensor product of symmetry actions on all the virtual legs and all the auxiliary legs. There could be more complicated ones. And in the end, what I'm going to say will also apply there in spirit, but probably there's more subtleties in the details. So that's one way to look at symmetry. So if I'm simulating the Ising model, it's natural to use a symmetric tensor. And the physical symmetry, this global physical symmetry will be reflected in a local symmetry of the tensor. Right? The tensor will transform like this. And it's easy to see that if you compose all these tensors, all the auxiliary symmetry actions will cancel out and you stay with a symmetric wave function modulo boundary conditions. Now, the other thing is if I look at topologically ordered systems, and I will talk more about that later in the talk, this is also characterized by symmetries, but now there is no physical symmetry action. Now the whole tensor is invariant under symmetry action on the entanglement degrees of freedom. And of course, I can combine these two things, right? I can say, well, basically, this is saying there is some symmetry on the auxiliary system. Part of it corresponds to a physical symmetry, and part is purely on the entanglement degrees of freedom. And that part corresponds to topological order. These can non-trivially interplay, right? It doesn't have to be a factorizing product structure. And then you would get things like SET phases. Now, this type of symmetry induces a next symmetry because we want to talk about order parameters. Order parameters are things which are computed in expectation values, right? I put an operator and I sandwich it between the cat and the bra state. So if I look at expectation values, I get something like drawn here on the very right? I get this tensor network sandwich. And if I look at each single tensor in this sandwich, this will inherit symmetries. So in particular, if I have these physical symmetries, right? I will put cat and bra together. The physical symmetry will cancel out, and I will stay with the same group action in the cat and the bra layer. So the symmetry group will be the same as before. In the topological case, I can sandwich these two equations and put independent symmetry actions on cat and bra because they don't couple through the physical leg. So I will get something very similar, but I will get independent symmetry actions on cat and bra, right? So I will get a double symmetry group G times G. And there can be intertwined version if I look at symmetry enriched phases, for instance. But the point is that all of these symmetries in the end pop up as symmetries in each of the local tensors in the partition function. So when we compute expectation values. All right. Now, what kind of order parameters can we measure in such a system? So we would like to construct these order parameters using all these symmetries, right? Not only using the physical symmetries or so. We see all these symmetries here in both of these cases, and we would like to use them as much as possible to construct order parameters. So what kind of order parameters can we construct, can we measure in such symmetric tensor networks? And let me look at actual order parameters, not disorder, so irreducible representations. And in principle, there's two types of things I can do in these expectation values. I can put my irreducible representation on the physical system, as shown on the right. This would be a conventional order parameter, or I can put them on the entanglement degrees of freedom, right? This would be, well, some different type of order parameter, presumably. Now, the point is that if I have a physical symmetry, like shown here on the right, and only then it makes sense to put physical order parameters, right? There must be a physical symmetry. This order parameter can be replaced by a different irrep type object acting on the entanglement, right? Because the commutation relation will be exactly the same. One time I commute with UG, one time with VG. So if it's an irrep, it's an irrep. It could not be numerically the same. That's why I wrote this equivalent here. But of course, if your auxiliary system is big enough, you expect to have enough access to your system to actually realize any O by any R prime. But even if not, when I said order parameters should transform in a certain way, the actual choice should not really matter, right? The actual choice is not what gives me the universal physics, it's the irreducible representation property. So what does it mean? Well, it means that in this case, we can push things down. It also means that in the other case, we can push things up. But pushing up is more subtle because pushing things up again from the entanglement level requires that there is a physical symmetry. But I told you, say in the topological case or SET cases, not every entanglement symmetry has a physical correspondence. Maybe there's no physical correspondence. So the safe bet is to take this here. So to only put your order parameters on the entanglement degrees of freedom. It will include everything you can do also if you put them on the physical degrees of freedom. And you want to allow these irreps on the cat and the bra level to transform in the most general way. And that depends, of course, on what symmetries you have, right? If the cat and bra symmetry actions need to be the same or not, etc. Right. So that's the order parameters we can build, right? So each endpoint of an order, each order parameter would be some irrep on the entanglement levels, either ket or bra or both.
Sorry, Norbert.
Yeah.
I missed this equivalence relation that you've shown on the right here.
Okay, so I'm saying if I want this O, so if this O transforms in a specific way, what I'm really doing is basically I'm measuring some object, so the total tensor will transform differently, right? So one way to think of that is to say that instead of putting the OA here, you say you have replaced the tensor by a different tensor which transforms differently. Kind of in the long distance regime, it shouldn't matter, right? What matters for order parameters is the transformation property under the symmetry. Everything else is kind of fine-tuned. So then this thing will transform in a certain way under the total symmetry here, but this will transform the same way, or maybe the inverse way. Maybe I have to invert alpha. One has to think carefully about that. But I'm also saying that if you have a generic system and your bond dimension is very big, actually there will be an R such that these two things are equal, right? Because in that case, if your bond dimension is very big, right, you have variationally obtained a tensor, the virtual system is much, much bigger than the physical system. So it should give you access to whatever you need on the physical system.
Mm-hmm.
But in the end, the real thing is that basically, what do you do when you measure 2-point correlation functions? At some position, you change your system. So what I'm really doing here is I should think that here I changed my system, right? And in the end, if I put a different tensor here, which transforms the same way as this object, it should have the same long-range behavior. And one particular choice of having a tensor which transforms...
Sorry, Norbert, can I ask something?
Sure.
So imagine we do the opposite. So we put the R on the virtual bond. I would expect that in general, it could be actually much worse than that. So it could change a lot of... so it should be equivalent to putting a lot of operator on the physical legs.
This is also true. I want to go like this. No, my point here is to say that I can take this and instead put something on, which is on the left.
Okay.
Which is exactly what you want. This is exactly analogous to what you're saying, right? Because I'm saying if I have this, I can always replace it by this. Mm-hmm. And indeed, you're saying if I have this, this could be much more rich than what I have here, right? It's maybe not always possible.
Okay.
But I think you completely agree.
Okay. Okay.
Do we agree?
Yes. Yes.
Okay. Good.
Yeah.
Good. I mean, but the real reason is not so much that. The real reason that we can't move this to here is that maybe there is no symmetry, right? Because it depends what system I'm looking at. If I don't have a physical symmetry, I only have entanglement symmetries. It will not be possible for fundamental reasons because there is no point in talking about the symmetry. Right, so that's one thing. The other thing is we can do is to look at these disorder parameters. So what disorder parameters can we construct? Well, again, so I didn't put the expectation values to make it not too messy, but in the end, what you should think of is that you want to sandwich things again, right? And I'm looking at one side of the sandwich where I put an operator. And one thing we could do is to put something like that, where we flip spins along a line, right? And ask what is the response of the system to that. We can do this in the ket or the bra or both, right? Depending on what situation we have. So when I write G, I really mean VG, right? The entanglement action of the symmetry. It's just I didn't want to write VG. Or I can do what we had before. I take an area, and on this physical area, I put this unitary. That's what we said before, right? This will give me an area versus volume law behavior. Now, if I look, so again, the physical symmetry is linked to an entanglement symmetry. So this means that in this case here, I can take this symmetry and promote it to an entanglement symmetry everywhere, but the V and the V dagger will cancel everywhere in the bulk, right? So what I'm left with is a loop of symmetry operations at the boundary of the region, which is really the same as here, right? Just that there are no open ends. So it's again an entanglement object, right? So what we see here again is we can take a physical object and promote it to an object on the entanglement. So again, we conclude that also for disorder parameters, it's sufficient to construct them on the entanglement. The most general thing we can get is something which is located on the entanglement level. And this could either be an open string or a closed loop of symmetry operations. Now, if you would ask me a bit naively, I don't have a proof for that, but I think it's true. Maybe, I certainly have good intuitive arguments, I guess. The intuition would be that the open string should be sufficient because whatever you can see with a closed loop, you also should be able to see with an open string, but the open string has more, namely it tells you what happens around the endpoint. We will see some evidence of that later. That's not fully formal, but somehow it tells you there is something here which is maybe not contained in these loops. And it means there's also something contained here which you cannot measure by measuring on the physical system. Okay. So what is the most general thing we can measure in a tensor network? So the idea would be that these should be strings, because I kind of said closed loops won't get us more information than strings. It should be a string of symmetry operations. Please tell me if I forgot to erase things. It should be a string of symmetry operations shown in blue with some symmetry in the ket, some in the bra, terminated by these yellow objects which transform like irreducible representations, alpha or beta respectively, right? And I compute this overlap. And in principle, I should be able to put any G and any H and any alpha and any beta. All of these give some information. There might be some connection between the different types of information, but in principle, all of these would be interesting objects to consider. And well, I guess you will see that if you ever did numerics with tensor networks, right? That's something which you can quite straightforwardly evaluate with standard techniques, contracting from the left, contracting from the right. Once you have a tensor which has these symmetries, so for instance, you did a variational calculation where you enforced these symmetries in the calculation. Now, one thing, and I will mention this, I will discuss this a bit later in the talk, there's an important subtlety in the construction of these endpoint operators because they're not unique. And normal order parameters, I said, are also not unique, right? We only know their irreps. But in the PEPs, there is a huge difference in that the only meaningful thing which is fixed is the way the symmetry acts on the virtual system. Nothing else is fixed. And that's very different from the Ising model, right? In the Ising model, not only the symmetry is fixed. The Ising model is the Ising model, which has more structure than the symmetry. And this is important. But let me discuss this later. But just to say that there is more to it than just this. Right. Okay, so we're slowly approaching topological order, but before getting there, let me just use one slide to argue that these kind of objects are maybe not only interesting for topological order, but they could even give us new, different, additional ways of probing systems, maybe even new information for conventional phases. We'll make a loop to that at the very end again. So what information could we access with these systems? So topological order, I will show you in a second, but my point is what happens with conventional phases. Well, I said earlier, one can study physical disorder parameters by acting, say, in the Ising model on some region with the spin flip operator, right? And then look at the volume versus area law. And this will correspond to putting a loop of symmetry operators in the system and measuring the normalization, the expectation value of that loop of symmetry operators. But if we put it on the entanglement level, we can take something which has an open end, right? And that's something which is not captured by a closed loop. The closed loop doesn't have an open end. And my claim would be, and I will show some evidence for that at the end, is that this allows us to probe, to access additional information beyond what can be accessed with conventional order like order parameters acting on the physical system. And I think that's actually remarkable that you can probe new things about the even the Ising model potentially using tensor networks, because you would think the Ising model has no surprises to offer. Maybe I'm being a bit mean to the Ising model. Okay, so but let me now talk about topological order because I also want to show some data and time is moving fast. Right, so topological order, as I said, is characterized by having some symmetry which is purely on the entanglement level. And if I move half of the symmetry operators to the other side, I get this equation here. And this is really telling us that if I have a string of these operators, I can move it through the tensor from one side to the other. And this is both found in explicitly constructed models, but also in variationally optimized tensors, one can recover this symmetry. Just to quickly advertise, we recently indeed could show something we suspected for a while, that in 3 dimensions, it's not necessary to have this symmetry to have topological order. So in the Toric Code phase, the symmetry would be, for instance, Z2, and this unitary would just be a matrix, which is sigma Z times the identity, right? So there's a +1 and -1 block. And the point of the symmetry is that the symmetry allows us to put strings, well, there's 2 points. One point is it allows us to put strings of operators, which we can freely deform. So such a freely deformable string cannot be detected by any Hamiltonian acting anywhere. So indeed, that's what you expect from topological order, that there are things which have an effect but cannot be seen locally. What you have to do instead is you have to put strings of these operators on your system, and you will see that the string can be moved, so it doesn't have any relevance, but the endpoints cannot be moved. So the endpoints will be excitations, which naturally come in pairs, and for non-abelian groups have non-trivial commutation relations. In addition, we can, on a link, put something which does not commute with that symmetry. Or differently speaking, I could take one tensor and change it for a tensor which transforms differently. Then the string will not commute, but say anti-commute. So if I take one of these different objects, I move it in a circle, right? So I move this thing here in a circle around the other one. Then removing the circle will give me, say, a -1 if they anti-commute. So I get some phase, right? Some braiding phase. So I get non-trivial braiding statistics from that. And in general, we can take these objects and combine them to get the most general excitation. And this is what we can consider. So a general pair of anyons in such a tensor network with symmetries will consist of a string of symmetry operations terminated on the left and right by 2 endpoints which transform like irreducible representations. I could also replace a tensor by one which transforms like a different irreducible representation. But in the end, if my bond dimension is big enough, that's what Luca said, right? Whatever I put on the entanglement level allows me to modify the tensor anyway in a very rude way because I have access to so many degrees of freedom. So it doesn't really matter in the limit of large bond dimension variationally what I actually vary. I will also abstractly depict it in the picture on the right. Just on the next 2 slides, I will talk about properties of pairs of anyons. So I use a simplified picture. But what it means, the gray thing is my tensor network, and I put a pair of these endpoints which behave like anyons. Now, of course, these objects are not necessarily eigenstates, right? So they're not necessarily particles. To get particles, I have to choose the right endpoint. It's right when I'm doing an excitation ansatz in a tensor network, right? I have to optimize my excitation. Otherwise, it won't be an eigenstate. So we need to address these endpoints to get eigenstates. Well, we'll see, maybe we don't want to get eigenstates for our order parameters. Even if I don't have eigenstates, of course, it still means that this object corresponds to a pair of anyons, which are dressed in addition with something trivial, topologically trivial, which, however, could make them dispersing, right? If I don't have an eigenstate, it will disperse. But if they're sufficiently far separated, these endpoints will still live in distinct topological sectors. The other thing is, and that's why we can even study topological phase transitions in this framework, is that even if we insist on keeping that symmetry, we can observe how topological order breaks down. If we change parameters in our system, the topological order in the system will break down. But the symmetry can still be present. I guess if you do it fully variation without imposing the symmetry will favor to go away after the phase transition, but we can decide to keep it. Now, how can we test for the presence of topological order? And we will see that this will lead us directly back to our order parameters. And to test for the presence of topological order, we would like to probe fundamental particles of these anyon-like objects, right? Which are maybe not anyons, but dispersing wave packets. But we would like to probe what properties they have. And there's 2 properties we can try to prove. So one property is that the anyon should be deconfined, which for me means the following. If I look at the normalization of this wave function with a pair of anyons, it shouldn't go to 0 as I separate them. So I should be able to place anyons at some separation. If you like this language, if not, ignore it. If you like it, you can say, well, there's some operator which creates anyons. It really creates them in pairs. So there's an A dagger I and A dagger J, which creates 2 anyons at I and J. Then I annihilate them again. And the idea would be that at long separation, this thing factorizes because it's a gapped system. And if it factorizes, I want that each of these terms, which is like an order parameter, if it factorizes, is non-zero. So it's a well-defined quantity if I put a pair of anyons in my, if I put one anyon in my system, this is a well-defined object, putting it and taking it out, right? It doesn't have norm 0. So it's really saying, in this tensor network, I can place a pair of these objects at any separation, and it will be normalizable. And this gives me something which allows me to say if the system is deconfined, one could call it a deconfinement fraction. And The other thing is that it could be that this thing, when it factorizes, actually goes to 0. It doesn't go to a constant. Then we would argue the anyons are confined. You can't separate them. So they are no longer topological excitations. But since it's a gapped phase, this correlation function will go to 0 exponentially. So we can extract a confinement length, or a typical length scale by which I can separate these objects. And if you look at what this indeed maps exactly to one of our expectation values, right? Namely, we have the same cat and bra symmetry string. It's a normalization of this object. The other thing is we can look at the overlap of a pair of anyons with a vacuum state, which is basically putting a pair of anyons and asking what happens. And this, as we separate the anyon, should go to 0, because then locally you only see one anyon. And if it's a topological object, it should be in a different sector, a different topological sector than the ground state. So this should go to 0. And then this should give us a length scale. And the inverse of this length scale should be something like a mass gap, like a mass of the anyon. I guess in field theories, that's basically a definition of a mass. Right? It's the correlation in field theories, at least, the correlation between two operators creating an excitation. Now, if this correlation function would go to a constant as we separate them, we would say, well, putting an anyon doesn't give us a distinct state, topologically distinct state. So the anyon has condensed. And then we can get a condensate fraction, which again would be the factorized expectation value. So it would be the expectation value of a dagger. And again, we can think, what is this in terms of tensor networks? Well, it's the overlap of the bare tensor network with the one where we inserted a string. So it again looks like one of the order parameters we have. So as we go through a phase transition, what do we expect to see? Well, we expect to see that as we approach the phase transition, there will be one anyon which condense, a different one which we will confine. The deconfinement fraction will go to 0. Here they're deconfined, so it's non-zero. The mass gap will close, right? The correlation function will diverge. And at the other side of the phase transition, we have a condensate fraction, right? And the other anyon will become confined. So we have some confinement length, right? It's not a free anyon anymore. So again, on both sides of the transition, we have an order parameter and a correlation length, and we can compute critical exponents. And this is very similar to what I discussed before with the Ising model, right? There's an order parameter, a disorder parameter. It doesn't really matter what I call which here in some sense, right? Because there's some duality relations behind in principle. But again, let me stress that to get these order parameters, we don't want to create nice eigenstates. So if we do this for anyons, right? We don't want to take the operator which at each point of the field creates an eigenstate. Because if we take this operator, we will not see anything interesting. We will see that this stays 1 and it goes down to 0. And one reason is that if we optimize this tensor, the endpoint of the tensor to get an eigenstate at a very, very large bond dimension, which is what we imagine gives the correct physics, right? Then we will influence a tensor network on a scale of the order of the correlation length, right? Because that's the degrees of freedom we can naturally access. And the correlation lengths will diverge. So it would be the same as in the Ising model, saying I'm allowing to take the optimal order parameter on a length scale proportional to the correlation length. And then you can get a step function, right? Just by adiabatically evolving your order parameter. Okay, I guess I should speed up a bit. So we started a bit late, but according to my clock, I have been talking almost 50 minutes. So I guess I should finish in the next 10 minutes. Is that reasonable?
Yeah.
Okay. Okay. So what is our approach to getting these order parameters? Well, we take some Hamiltonian, we variationally optimize our tensor network. So we just do a variational TEPS algorithm, but we enforce this topological symmetry for the phase we're looking for. Now, this is a very small restriction. If it's a Z2 symmetry and we choose the same bond dimension for each of the two irrep blocks, this only reduces a factor of 2 and we go up to bond dimension 6. So we have 20,000 parameters. So a factor of 2 is then still 10,000 parameters. So it doesn't reduce the number of parameters too much, right? It's not a super strong restriction in a variation sense. And then we extract using standard techniques exactly these anyonic order parameters, right? By contracting from the left and the right, looking at the fixed points, and then having some channel operators where we can compute these objects. So the spectrum of this operator will give us some correlation length corresponding to that thing, and take the fixed point from here and here, and computing the endpoint operator will give us order parameters. So the thing you have to toss in is to take your variational method and kind of project it or enforce it to stay in the symmetric space. even though actually if there's no numerical noise, it should stay in the symmetric space anyway, because there's no gradient pointing out of it. Now, a key question, I'm not sure I really have time to talk about that, is how to choose the Anyon operator. So the Anyon operator, the endpoint. The endpoint is an irrep, and the irrep has lots of degrees of freedom. And in the end, this is not specific to topological order. It's a general problem. And the point is that the end, all we know about the endpoint is the anti-commutation relation. This gives us lots of degrees of freedom. So for the Ising model, for instance, it could be any operator in the YZ plane. In the Ising model, that's not an issue. And why is it not an issue? You pick any operator, you fix it, the Hamiltonian changes smoothly, you're fine. If I do variational tensor network methods, there's a gauge ambiguity, right? I could take any tensor and replace it by a tensor with some gauge transformation. And in the specific case, all I need is the gauge transformation commutes with the symmetry. Within each irrep, it can do anything. And this is somewhat uncontrolled a priori. And this would be the same as saying I'm taking the Ising model, and for each value of the field, I do a random rotation in the YZ plane, right? You see immediately this completely breaks your order parameter, right? Because you get randomly jumping phases. So you need to stabilize this. And this requires some gauge fixing, but in the light of time, I won't talk about that. You can ask me. But that's actually an important addendum, right? You need some gauge fixing, or you need to be very careful with your tensors to avoid that your gauge fluctuates in an uncontrolled way. So we use this to study the Toric code in magnetic field, X and Z field. So this has a topological phase, trivial phases through two different mechanisms. Either fluxes can condense or charges. And it has a self-duality if we reflect about the diagonal axis. And the two lines with field only in one direction map to the 2+1D Ising model, the 2D quantum Ising model. There's an exact mapping between the ground states. So we know something about these models, but what is of course less clear is what happens if you move diagonally. There you have to do more hand-wavy duality mappings to argue that it should map to something like Ising type physics, 3D Ising physics. And let me just show you what we got. So we studied these four lines here. So we studied these lines here, 1, 3, 2, 4. And so the first row of the plot, the plots in the first row show these two transitions, which are magnetic condensation. And the second row shows these two plots, which are electric condensation. And the two plots which are on top of each other are dual to each other. So you should show the same behavior. So here you see that, so on the left, this shows the deconfinement fraction, because the electric particle gets confined, the magnetic gets condensed. And you see if our bond dimension is 4 or 6, it already looks pretty converged. Bond dimension 2 doesn't work, but 2 just doesn't have enough parameters because each irrep is one-dimensional. And you see that the other transition shows a very similar looking behavior, but doesn't have the same values of the order parameter. And if you compare, for instance, these two lines, which are dual to each other, so the gray line here is actually a copy of the line from the top, right? So the gray line here copies the line from the top. You see you get different curves for these two dual lines, but it's not surprising because the way the gauge fixing works is different, right? In one case, so this is a string operator, and string operators have a unique gauge fixing. You just put the identity at the end, right? Because there's no irrep, and the identity is gauge invariant. It's the only gauge invariant operator. Electric charges are irrep-like objects. They cannot be gauge invariant. You have to make a gauge fixing. And the gauge fixing changes the curve, but that's not the point, right? As long as we see the same scaling behavior, I mean, the value of the order parameter is not meaningful. The scaling behavior is meaningful, right? And that's what we're interested in. You also see it's very asymmetric, right? The deconfinement, the thing on the left of the phase transition, that small field, the topological phase is extremely steep. And the other one is very shallow, right? So there's quite some difference. So let's look at the critical exponents. So if we look at the condensation critical exponent, the shallow one, we plot this for all 4 possible transition lines. And you see these critical exponents all have the same slope in a log-log plot. And the slope indeed fits very well the data we know from the 3D Ising universality class, right? So this really very nicely matches the known value from the 3D universality class. I mean, this value is not a fit, right? This is a known value, but you see it matches very well. So this is what we expect from the 3D Ising class. So it really confirms that also along the lines 3 and 4, which don't map to the 2D Ising ground state, 2D quantum Ising ground state, you really get the same critical exponent. Of course, this was generally believed, but the evidence was only through very indirect duality.
Norbert, Can I ask you something? If you wouldn't know that there is a duality, how would you see it from your numerical data? So would you be able to discover that actually these two lines are dual one to the other from your numerics?
No. I mean, what you see from the numerics is that the whole phase transition line, so the whole line, if you look at the phase diagram on the right bottom, right, there's this phase transition line. You could see that wherever you go through this phase transition, you have the same scaling exponents. So you would say it's all the same universality class, but it doesn't give you a duality mapping.
Okay. On the other hand, you should be able, for example, if you take the overlap.
In some sense, it's a stronger possibility, right? To be able to say it's the same universality class, even if you don't know how the duality mapping works.
No, I agree. But imagine that now you take the overlap of the two-wave function, they should be the same, right?
Say again?
So what I mean is that it's duality is stronger than being in the same universality class. And it basically means that you should have the same ground state, no? Because all the correlations.
No, but the duality is kind of non-local, right? It's this Toric Code to Ising model duality is going from loops to plaquette colors and things like that, right?
You're right. You're right.
The thing is I think that the self-duality has the same issue, right? Because if you go to Ising, then you look at the duality of the Ising and you go back. And the duality of the Ising is non-local in the end. Right?
Yes, sorry. Yes.
Has some non-local features. So I don't think it's so easy. It's also not a Hamiltonian duality. It's really a constant duality. Right, so we can also look at the correlation length. And there we can look at, well, on the one hand, the mass gap which closes, on the other hand, then the confinement length, and both have the same critical exponent, right? Which again matches the Ising critical exponent very nicely, which you can see in the inset, even though not very well. But now comes a really, so this really demonstrated the whole thing is in the Ising universality class, really by seeing the critical exponents, not having to go via some dualities. I mean, the duality to the Ising model in the horizontal and vertical line is completely fine, but the other one is it's a bit tricky, right? You have to make some assumptions about what you get. But now comes the interesting thing, what happens for deconfinement? So if you look at the deconfinement, we also see universal behavior, the curves along the different lines. Again, this is all 4 possible lines, right? This is lines 1, 2, 3, and 4, all have the same slope. But the extracted exponent, this should be taken with a relatively large error bar because it's very small. It's very small. It's 0.02, right? And it's an order parameter, but it's nowhere close to anything which is known, right? So in some sense, it's a very mysterious thing. And we have some, well, I will provide a few explanations what it is. In particular, it's something you should also be able to see in the actual Ising model if you use PEPs, not if you use physical observables. And given it's the Ising model, it should be related to beta and nu because there's only 2 scaling dimensions, only 2 primaries, right? So all the data can be extracted as a linear combination of beta and nu, or sorry, as a combination of beta and nu. But nevertheless, it shows that there's very, very surprising physics going on. So to say, if you look at these order parameters, they show very different critical exponents. And okay, I guess that's now the last slide coming. Let me try to explain a bit what's behind this this object. So what's the nature of this critical exponent, which is something like 0.02 plus minus, I don't know, 0.005 or so. That's will be the error bar. And we can ask what happens along the line where we put one of the 2 fields equal to 0. Because there we know we can map it to the 2D quantum Ising model. And what this shows is that this order parameter maps to an Ising model where we have optimized our tensor variationally, imposing a Z2 symmetry, right? And where the order this order parameter for deconfinement now maps to a disorder parameter, where along a cut, along a cut we put a symmetry operator and terminate, and then we take the string to infinity, or we take a very long string and ask what happens as we separate the endpoints. And we compute the normalization of this object. We compute the we compute the normalization of this object indeed. Right, yeah. So we compute the normalization of this object and compare it to the normalization without the twist. And you can see that kind of a cartoon picture in the paramagnetic phase is that the entanglement degrees of freedom are decoupled basically, right? You just have a product state. And then it doesn't matter what you do there, right? Because the symmetry will act trivially. So nothing changes. So it's 1. And in the ferromagnetic phase, you will say, well, if I have a GHZ state, these are delta tensors, right? Kronecker deltas. So then these two states will have to be the same, but the Z will flip them, right? It's kind of a spin flip symmetry. So they will be orthogonal, you will get 0, right? And then again, if you have something in between, you expect to get something which comes from the endpoint, right? So in the disordered phase, you expect some penalty from the endpoint, but you won't be able to see the string. So you expect this to go to 0 in some way. And you could say, well, this should be related to these disorder parameters, right, which have been also studied recently, where you apply a symmetry to a certain region, and then you compute the expectation value of that. This gives you a closed loop, but now you compute the overlap of this closed loop with a ground state. It's a different object. It's not a normalization, it's an overlap. And actually from some Wick rotation arguments, you might conjecture that they're the same, but the point is that here, what people have observed is that the critical exponent for this kind of thing is actually equal to the critical exponent for the correlation length, 0.62, right? And what we saw is that we get this beta equals 0.02 here. So this is vastly different. So it seems that this indeed gives a completely different information, or it acts as a completely different parameter than the other one, which also makes me a bit suspicious that these type of duality mapping Wick rotations arguments sometimes can actually fail. And the point is that if you do these duality mappings, so if you take this kind of thing and you say, well, let me write this state as a partition function at very low temperature, this is an extremely anisotropic partition function, right? And you're looking at the extreme anisotropy limit, right? Because you're trotterizing imaginary time evolution. And in this partition function, this would basically be a membrane with an endpoint, right? So you're basically indeed looking at like a Wilson loop, which you make infinite, but in this extremely anisotropic model, right? If you dualize H theory. And it seems that indeed this anisotropy has an effect and you get different exponents depending what anisotropy limit you take. And I would be very interested to understand this better if anyone has any idea. A somewhat not really educated guess we had was that this beta star is nu eta divided by 2 with eta the anomalous dimension. This gives roughly 0.01, which given the accuracy and it's so small is not completely off. It's maybe a bit outside reasonable error bars, but not completely off. This guess would also be consistent with what we see for toy models, which map to the 2 plus 0, the 2D classical Ising model, and with the mean field ansatz. Now, one interesting thing is that we had computed this previously for explicit models, which directly map to the 2 plus 0 Ising model, right? Like Toric Code with string tension. And we got that this was equal to 1/8 equal to beta. But this is basically a manifestation of the self-duality of the 2D Ising model, right? And there's no self-duality of the 3D Ising model. And that's kind of what's going on, right? Basically, these two things should be dual to each other, but since a 3D model doesn't have the self-duality, you get something different. You get some object which somehow should show up in a gauge theory as well, right? If you use this, the duality of the Ising model should give you some gauge theory, and there it indeed should correspond to some Wilson loop operator. And it should correspond to how the prefactor of the Wilson loop operator vanishes as you move from an area law to a volume law. Kind of how the area law prefactor should vanish. That's kind of the guess, but we would like to look more into that. But I think it's nice to see that beyond probing topological models, such things like twisting the entanglement in this way gives you actually access to maybe additional probes for these kind of systems. And with this, I'm at the end. I guess I've talked enough, so let me just summarize.
Sorry, Norbert, on the previous slide, isn't it just the monopole condensate in the gauge theory picture?
Good question. Maybe. I'm not a gauge theory expert. I tried to find this critical exponent. I couldn't find it anywhere. I would certainly be very happy to see that it shows up in some context.
Okay, maybe I can give you some references.
Sorry?
We can check some references to actually see.
That would be great. I'm certainly extremely interested. Okay. As I said, the problem if you map it to a 3D model, right, is that you have to totalize basically you want to totalize e to the minus beta h, right? And then you have the string which gives you like a half plane. But the totalization is extremely anisotropic. And it seems that this matters. I don't know. I mean, kind of what we're doing is that we have this 3D system. So this is space, right? This is imaginary time. And then putting this plane of z's corresponds to putting a half infinite plane here, right? So this is infinite open boundaries or whatever. Well, maybe in the time direction, I have to terminate it somewhere. And you're looking at something like the expectation value of this thing here. And so what should only matter is the boundary here. So you're applying the symmetry everywhere here, but if you do a duality mapping to the gauge theory, you should only be left with the endpoint of this, right? So you should be left with something like a Wilson loop string here.
Yeah, it's typically called a Polyakov loop.
Exactly. And the thing is, of course, you would say, but this is exactly the same as a loop which lies like this, and where basically if I have symmetries attached to it, they go down, which is the other order parameter, which has a different critical exponent, which is eta. But the point is, of course, the coupling in this 3D model is extremely anisotropic. You have a super strong coupling in the space direction, right? And an extremely weak coupling, wait, the other way around, right? You have a super weak coupling in the Ising model in the space direction and a super strong coupling in the time direction. And you want to take an extreme limit of that, so to say, right? Because it comes from a totalization step, which shows up as a factor or as an inverse. And apparently this makes a difference, right? Because we get this extremely different critical exponent from what the other guys got who looked at this kind of order parameter for the Ising model. And they say they get nu, which is 0.6 and 0.6 and 0.02 are, you know, vastly different. So people keep telling me that it shouldn't depend on the anisotropy, but my feeling is if you take the limit of extreme anisotropy, it might actually matter. But I think it would be great if there would be any literature where people have looked at a quantity where one can be sure it's the same quantity, right? Without too much hand waving. And then one could compare. Or where people look at quantities with hand waving, but they get a similar number, right? That could be a good evidence. But I'm a bit suspicious if people say there's a hand waving correspondence, but then the numbers differ by a factor of 30. Then maybe the correspondence is too hand wavy. Okay, I guess this is a great time to stop. Okay, key point, if you want to look at order parameters in tensor networks with symmetries, use the entanglement degrees of freedom, you get access to more things. You can use them to probe topological order and get information about critical exponents at the phase transition. But in addition, it might even be useful to probe conventional phase transitions like the Ising model and get extra information. For the Ising model, it probably only gives you things which depend on the scaling dimensions of the underlying Ising CFT, because probably there is nothing which leads you out of the Ising CFT, even with this construction. But for other models, it might maybe give you access to more things than two critical exponents, right? It might actually give you access to a third piece of information if there is more than two primaries. Okay, thanks a lot.
Okay, thanks, Norbert, for this nice talk. Any other questions?
Sorry, how much is 2 beta over nu in this?
Say again?
2 beta over nu. How much is that?
Over nu, why? Okay. Oh, so
typically this is the value of the disorder parameter exponent.
Okay, so my guess was this one, right? Which is the anomalous dimension, which I forgot is what, 0.036 or so. I mean, my initial guess just from numbers was that it should be the anomalous dimension divided by 2 because that's 0.18. But then indeed Andreas Ludwig convinced me that it should contain nu. Which is reasonable, right? I mean, again, yes. this guess is not particularly educated, but it's not randomly made up, right? I mean, what you want to know is if you have a cut along which you put the symmetry twist in the Ising model, how does a correlation function decay at the critical point? The guess is basically based on saying this decays like 1 over the distance to the eta plus 1. If you don't have a cut, right? If you just compare two spins at some distance. But then you want to integrate this over a slit. And if you integrate this, you would expect something like this. And if some correlation decays like this at the critical point, then the beta should be exactly this, right? Whatever the exponent is divided by 2 times eta. Because this basically introduces some length cutoff which you insert in B. That's at least the argument Andreas Ludwig gave me for relating things at the critical point and of criticality. But again, it's very hand wavy, right? But at least it seems to have some consistency, say, with a 2 + 0 decays. But if anyone has any good guesses for that, I'm extremely interested. I mean, one feeling I had is that people in gauge theories often don't compute critical exponents because, you know, you don't necessarily tune coupling parameters and ask how does a physics change, but you're interested in actually in a specific point, right, which actually describes your system. So people were talking about these kind of plane-like operators and so on, but I didn't really find any critical exponents.
Okay. Yes, I'll send you some references.
Perfect. You can also hang out here.
Okay. Any final questions? Well, if not, I would like to thank Norbert again.